Hi everyone. Today we will examine some application examples of the fuzzy logic, and we will end also with the examination of or the analysis of the ANFIS editor. So it's the so-called adaptive neurofuzzy inference system, because it is a powerful tool that allows to obtain the model, the fuzzy model of a system, or in our case, it will be the model, the description of the controller, directly from the input-output data. Then it represents a very useful and complete tool for this kind of examples. So let's see some application examples of the fuzzy logic. And for example, well, it's the same. It can be the same application also that we saw for neural networks, because as an example, a neural network or an inference system is able to, in this case, to help the people or the teller working in a bank to agree for loans to the clients, and on the basis, as is shown here in this picture, on the income of the person and the monthly costs. And so it will provide, on the basis of a rule-based system, an advice, so a suggestion that can, if this person is reliable to return back your loan if is agreed by the bank. So, for example, the monthly income can be divided on the basis, for example, of no income at all, a small, middle, large, or very large. So depending on some reference example of salaries. So an example, we have for the case of 3 rules that represents, they are quite intuitive, because, for example, if the income is very large and the monthly costs are small, so then the advice give credit to this person. The second rule can be, for example, if the income is small and the monthly cost is middle, then it's a boundary case, because we don't know how much the person will be able to return the loan. Or for the case of a rule tree, well, pay attention, because the first two rules, they have a connection which is represented by the logic connection and the third one is as a or. So if the income is middle, so it means that it has a good salary, and or the monthly costs are small, then the advice probably give credit. And this fuzzy system is normally realized or implemented as a system represented by this module. Of course, the inputs are non-fuzzy inputs, because normally you feed the system with the real income, which is represented by a value of the salary, and the monthly costs are represented as the same, or with some value of money. And then this fuzzy system should provide a conversion of the non-fuzzy inputs into fuzzy variables, and then another conversion from fuzzy variable to non-fuzzy output. And in this case, because the income is the middle and the monthly cost is small, only the second and the third rules can be applied, and we can see here an example of the firing system of the rules. So we have the income is as represented by this membership function, and which is fired represented by this line, and we have the monthly cost, which is small, so it's firing with this value, and according to the connector and which can be in this case implemented by the mean value, a norm. So you have an advice which is represented by this membership function. And for the third rule, so the rule 3, we have the income is represented, so is fired in this, so the large, and the monthly cost is represented by this membership function. And because there is the connector OR, so you are taking the maximum between the two values, and you obtain the advice represented by this fuzzy system. And then in order to have a numerical value, you defuzzify your fuzzy sets using, for example, the center of gravity rule, and so you obtain the case of a boundary value, so 0.45, which is something that it says that perhaps you can have or not the reliability of granting a loan. And if we want to describe this value representing in mathematical as a mathematical relation, you have this expression where is referring to the loan, is using the values of the fired membership functions, and depending on the, for example, the value of the input, and of course the constant, and previous values, it depends on the cost of the person, averaged by the number of total membership functions. Well, another simple case that is also the same, is quite simple, is represented by, well, is a very traditional application of fuzzy logic, because this solution was already available in, let's say, at the beginning of the 90s. And you can see that you can also understand that a fuzzy control can be used in this case for controlling a washing machine, and in particular, your control, of course, is solving the problem of the selection, perhaps on the depending on the level of the dirties of your clothes that you are entering into the washing machine, is controlling the program, and then on the basis of the program is also regulating the, for example, the speed of the motor. And this is, as for the case of the spin dry process, and of course the energy, you have a first control, which is using the energy, and perhaps the breaking time of your program, so it implements the first regulator, and depending on the load on the system, so depending on the load and the program, is another controller is taking into account the rotation variation depending on the for example, the level of the load and the type of your cloth, and then it generates what we call spin dry curve. Well, the spin dry curve you can see here is the behavior of your of the cycle in terms of rotation per minute, and depending on the inputs you can obtain different curves as a function of the time. Well, another example is represented by the fuzzy vacuum cleaner is another powerful application of fuzzy control in order to optimize a vacuum cleaner, and in order to obtain also good performances in terms of the working condition. And you have different modules that implement this system, in particular the pressure control, which is allowed to regulate the level of the vacuum produced by of your vacuum cleaner. So you have a pressure control, or the dust sensor, depending on the filling of the tank of your vacuum cleaner. And this system is also able, for example, to provide a monitoring of your process in terms of when you need to change the filter or the blockage of your process. So you have perhaps your pipe here used for blowing or removing the dust, and you have the dust bag. So you have a pressure sensor, a dust sensor, which can provide some details or some information on the level of the working condition. You have the pressure sensors and also the motor, and which is driven by another controller. And we have here the control of the system, so of the whole system. So you have a motor. Of course, the motor is actuated by a triac and a controller. Well, the motor is actuating the blower. So depending on the blower, on the basis of the blower, we have the dust sensor, and which together with the temperature sensor, depending on the motor level, temperature of the motor, is generating something that can control or regulate the level, the reference of the pressure, and depending again on the pressure sensors inside your machine, you can provide another reference in order to control the best conditions for your motor. Another important example is represented by the automatic transmission systems. It's something that, if you think about it, is quite difficult to generate or to develop a controller on the basis of on the values of your reference variable. So in fact, in this case, again, a fuzzy controller is really powerful in this case, because depending on the conditions of your car or the driving conditions of your car, so which depends on the driver, so depending on the style of driving, and also the driving situations like overtaking curves, mountains, or the background, the city, land, highway, and again the working condition of your car is very close to the working condition of the washing machine or the vacuum cleaner. So the motor temperature or the load of the vehicle, they represent all external conditions for the car. So depending on the, for example, in this case, on the slope of your car, of your road, so you have different curves here, which are represented as a value of a reference value of the speed of your engine, and depending on the shift, so you have a different curve here, and depending on this curve, you have also the changing of the gear, which are decided on the basis, for example, here of the slope of your road and the speed of the vehicle. So a simple model of the vehicle can be represented in this picture. So we have the relation of the function of the gear and of course the acceleration which produced the force on the vehicle. We have here, so the force produced by also the engine. We have the vehicle model, which is a very simple first order model for the velocity. And then we have here the position, and on the basis of the force acting on the vehicle, here the vehicle models with the, especially here the mass of the vehicle, and we have, for example, the load resistance depending on the velocity of the vehicle, which should be compared with the velocity of the air, and we have the climbing resistance, so this depending on the slope here, alpha, so is the slope of the road, the roll resistance and the load resistance, which of course note that the load resistance, the resistance of the load depend on the speed of the vehicle. So we have this model which provides the input of the engine, and the output is the velocity and the position. So the automatic the automatic transmission system can be represented as a fuzzy system depending, for example, here on so depending on the slope of your road or the opening of the throttle. So you have here, it can be intended also the power generated by your engine, and you have the change of the throttle opening, the rotational speed of your engine, and the change of the rotational speed, because if you remember, a fuzzy PID controller depends on some values of the variables and their derivatives. So you have you can implement in this way a fuzzy PID controller, and then you can take into account the net force acting on the system, the brake, and the actual gear. So you will have a fuzzy rule-based system which evaluates and also depends on the vehicle load, the driver type, the shift control, and you can, if you remember, the curve which depends on, for example, the slope here of the road, or the throttle, which in turn depends on the speed of the engine. So the vehicle load can be light, moderate, heavy, very heavy, and the driver type can be economic, sportly, conventional, or in winter, and shift control can be fixed, down, forbidden, or allowed depending on the driving conditions. This is an example of the membership functions on, for example, or for the wheel, so the speed and the gas pedal, so which is linked to the throttle opening. And some rules, so if we have, for example, some variables are negative and then the load is downhill, or if the variable is still negative and the brake is pressed, then the load is downhill, or the input is positive and the brake is unpressed, then the throttle is open, then the throttle is open, then load is uphill, or you are going up, and so on. You have different working condition. And for example, another, which depends on the condition. So if the gear is in the first position, then the shift down is forbidden because there are no other lower gear values and so on. So this is an example of some rules depending on the values of the force here. For example, the F, as is represented here, is if the delta of the force is negative, so it means that we are going in downhill, or again, if the delta of the force is negative and the brake is pressed, then the load is downhill. Or if the delta force is positive and the brake is unpressed and the throttle is open, then the load is uphill, we are going up, so depending on these values. And of course, you have also the road profile represented in this picture, and the driver model, which represent in principle the values of the throttle opening. So this is the reference, for example, for your model. And then you can consider the vehicle velocity depending on the drive shaft revolution. So it's increasing, decreasing, constant, depending on the driving cycle. And you can have here a picture of the behavior of a shift as in a traditional, which is conventional. And there are some, when you are using, for example, conventional control, there are some disadvantages. For example, in some cases, the shifting back can be late. And when you are using a fuzzy model, you can see here that there are some advantages that you can improve, or it can improve depending on the two. You can see here that is reducing in some cases the size of your shift behavior, so you can delay the shifting up, so it improves also the driving cycle. It can introduce early shifting back, for example, in the mountain, and shifting back by downhill. So it's something that it can be implemented in this way. So we have the fuzzy controller, which is using as a primary controller variables the velocity and the change of the velocity, which is computed here for depending on the engine, which the engine is a dynamic model, which depends on the air valve opening position and the ignition of the engine, which has a reference value, which is controlled by the fuzzy controller, and we have a reference of the air valve error here, and we have a reference, a nominal value, which is computed by this module, which is devoted to the calculation of the nominal idle speed, which of course in turn depend on the throttle angle, the temperature of the engine, and the engine speed. And of course, a second type of, well, this is the speed controller, and then you have the cruise control, which allows to maintain, for example, the velocity in a constant value in front of variations, for example, of the road, the load conditions. So you have a an upper controller, which is represented by the fuzzy supervisor, which is computing the reference value of the air valve and the reference velocity, the reference, and then is used some average values of the throttle opening, which is used by the actuator and in turn to the vehicle, so the vehicle is generating the vehicle speed and the reference. So we have the velocity error depending on the fuzzy, the inputs of the fuzzy controller, and then we have the closed loop of the system. And we have here is another way of an anti-knock control, which is represented by this picture. So depending on the slope of this line and the values of K2, we have two different conditions in the noise. So wake noise or intensive noise, rising note, or intensive note. And another example is represented by the car electronics for the case of electrified vehicle. So we have electric power steering, hybrid motor in the case of, so we have an automatic transmission, the shock absorber and the level control, and we have a four-wheel steering or four-wheel drive, depending on the kind of the type of your car. So we have the sensors are used for identify the different driving situations, and then an adaptive systems is used, for example, in the control for controlling or actuating your actuators. So, and for the case of the driving situation identification, we have the data that provide the conditions of your vehicle. We have a buffer of your signals. We are performing a filtering or a pre-processing of your signals in order to remove some unwanted disturbances, and then we can use a neurofuzzy system, because a neurofuzzy system is something that can be used for identifying your current driving condition, for example, and depending on the kind of data, we can, for example, for the case of signal processing, we can use a fuzzy system, and is integrated with the neural network, because, for example, the neural network is processing some video information from reference data. So a neural network, or especially a deep neural network, is integrated in this system. And we can have different driving situation classes. For example, very high speed, continuous driving situation, straight section, low lateral acceleration, no steep climbs nor descents. For example, this is the case of the freeway. Class 2 can be identified with the high speed, continuous driving situation, straight section, low lateral acceleration, no steep climbs nor descent. So, for example, highway or local road. Class 3 represented by high medium speed, continuous or discontinuous driving situation, possible high lateral acceleration and or steep climbs or descents. For example, curvy hilly roads, transition between class 1 and 2. Then we have the case of low speeds, often discontinuous driving situation, high traffic density, medium or no lateral accelerations, medium low climbs or descent, for example, downtown, stop and go, outer city area. And the last class is represented by the very low speed or stop traffic light intersection parking. So we have the different system components that are represented by the inputs are numerical values. They are phasified depending on the number of reference of the fuzzy rules or the fuzzy membership functions, small, medium, big. And then we have the inference system, which is implemented by means of the if-then rules, different depending on the number of clusters. And then we have the phasification and then the generation of the inputs. Well, the phasification layers, it depends on the membership functions. In this case, the membership functions depends on the center and the width. So depending on the input and the bias, it is generated, and the input, the fuzzy value, the phasified input is generated. The evaluation of the premises is obtained as a composition of the rules. So for the case of the product, when you are considering different rules, and or you have when you are considering the case of the rules, you have the or conjunction, and then you have this complete system of the evaluation. And then the inference and the phasification, because the inference you have a max dot because is a or operation, and you have the phasification, which normally implemented as a center of gravity of the center of sums, the phasification, and this is the representation, the numerical representation of analytical representation of the output. And then so the complete network can be, or the complete system can be represented as an integrated neurophasy, because you have a phasification, an inference, and the phasification of your inputs as with a structure which is very close to a neural network structure. So we have a topology which is represented as a neurophasy system. So finally, we can think of an integrated tool, because you have an expert, or the designer is using a fuzzy development tool, so the fuzzy logic programming file. You have a decoder which converts, for example, the neural network to a fuzzy system, and you have the fuzzy development tool and the fuzzy logic programmer. So you have a coder that decides or that optimizes the weight matrices and generates the simulation environment for the neural networks and the reference data. So we have this integrated fuzzy tool, which is represented by the fuzzy logic toolbox, which allows you to generate, to set your fuzzy membership functions, to decide the input and the outputs, the kind of the different parameters in your system. So we have, for the case of, for example, with 4 variables, the number of 4 membership functions, very low, low, high, very high, which are distributed in this form. We have 4 outputs, 4 output variables depending on the driving situation classes, 2 membership function, low and high. So we have the phasification for each class, and then depending on the input, we obtain a rule base which is generated by a number of, in this case, we have 95 rules because we have four input and 4 membership functions, and depending on the number of classes, we obtain this number of rules. And of course, the optimization parameters are represented by the centers of your membership functions, their width, the rule weights, and the consequence. So you obtain, depending on our inputs or the driving conditions, if freeway, highway, road, city, stop, we obtain this accuracy of your driving cycle, and these represent the outputs of your system, depending on the time and the driving conditions. And so you have the comparison of the initial system and the optimized system, and you can see that the improvement in your optimized system. Another example, interesting example of the use of a fuzzy system can be exploited, for example, of fuzzy parking control, where the fuzzy is used for integrating all the possible information, or for example, on the weather, on the conditions or the period of the year, of the hour. So it provides the information on the status of your car park. For example, this is full or is free. And of course, the conditions of your parking, of your car park, depends on the number of cars that are entering and go out from the garage park. And so you need a very accurate system in order to provide what we call prognosis of your process. Of course, it depends on the traffic density. The time is very important because it depends on the time of the day, so early afternoon, midnight, the day of the week, because it's a working day or is a holiday, or again a season, the season, Christmas, summer, sales, weather conditions, cold, rainy weather, people tend to go to large shopping centers, so for example, the car park can be full, or very hot, sunny weather, many people go out of town, so perhaps the car park is empty. We have special traffic conditions, for example, roadworks, holidays, or special events, like in the case of concerts, parades, processions. So the kind of parking carriage we are considering for this example is situated downtown, near to the shopping center, mainly used by people that go shopping. Well, we have a short time park during the day with a low percentage of long-term parkers because it's near to a shopping center. Cannot be filled within 1 hour due to the structure of the garage And we have data from 10 parking garages in Düsseldorf, Germany. So this represents also a real test case. And we have the weather data from the Weather Institute in Offenbach. So it means that we have also an integrated data information system. So we can analyze depending on the number of parking lots, which is about 300, and the number of occupied place. You can see here that depending, of course, is empty, or we have a low number of long-term car park, and then is increasing up to the maximum during, for example, near the lunchtime, and then is decreasing, and then we have another peak here, and then is decreasing during near to the evening. And this is the number of cars driving in and the number of cars driving out. So when the number of cars driving in is bigger than the number of cars driving out, the number of occupied places is increasing, and is the opposite when the number of car driving out is higher than the number of car driving in. So the car park is reducing, and you can see here that the inputs and the outputs of the system, so it depends on the day of the week, the time of the day, the season, the holiday. We have a role-based system which is evaluating the day of the period of the time, and also considering the weather. So the weather, which is selecting the temperature, the rainfall, sunshine, and then we have this information is fed to the, for example, together with depending on the temporal need, the traffic density, the number of cars driving in, driving out, the capacity, of course, is something that is constant, and we have special situations. So we have the main rule-based, and it provides a forecast of the car park occupancy. Some examples of rules. For example, when the weather is nice, so hot, not rainy, sunny, it will be relatively quiet downtown in comparison to other weather conditions. So we have this kind of rules. If the temperature is high and the rainfall is dry and the sunshine is sunny, then the weather is small traffic. So normally, perhaps people are not using cars, or in a normal day, for example, Thursday evening, shops are open, not on a holiday, not during the weekend. It is relatively quiet during the evening. This is independent from the weather because there are no cars entering the car park. So when we have some rules, it's not an holiday, it's in the evening, it's not a weekend, it's not Thursday, then the temporal need is low. Or another rule which expresses the prognosis for the time after 1 hour. So if the parking garage is almost full and is expected that many vehicles are driving towards the parking garage, then the prognosis is that it will be full within 1 hour. So this is the rule. If the capacity is critical and the temporal need is high, or the temporal need is very high, then the forecast, the garage, perhaps it will be full. So normally we can use a clustering system with a neural network, because depending on the data, we can generate so the network can generate the input for the fuzzy system, and then using a clustering of the data, we can obtain these the final results. So we have a prediction which is very which is very useful because we can provide a forecast of the capacity of the occupancy of your garage depending on the data we are using. So after using the described method, we have an 8 from 78. We have an increasing on the prediction quality of 86-89%. And if we continue to improve our tuning of our process, we can obtain an accuracy up to 93%, which is really high. So in order to conclude this, just this is a very simple or just a remark lecture how we can use a fuzzy system in our application, and if we can do it, it represents a very important and powerful solution to our problem and to the tuning, for example, of a traditional control. Okay, thank you for